The hum you hear is not just the sound of progress. It's the roar of an inferno, contained deep within these vast digital cathedrals. The artificial intelligences we read about, like Almo 2, are growing at unimaginable scales. We talk about models with 7, 13, even 32 billion parameters, striving for perfect stability and unprecedented efficiency. But that scale comes at a cost, an astronomical output of raw, brutal heat. Most people imagine AI as ethereal code, a whisper in the cloud. But they're wrong. It's an intensely physical phenomenon, a relentless furnace burning through silicon, threatening to melt the very infrastructure it runs on. For decades, the cloud computing backbone, where these AI giants live, has relied on a surprisingly simple strategy: massive fans and air conditioning. We pump freezing air through raised floors, push it into server racks, and hope it absorbs enough heat before exhausting it out. It's a game of scale and brute force. This approach works, to a point, for general computing. But AI's appetite for power, and its corresponding heat signature, is fundamentally different. It's like trying to cool a volcano with a household fan. Current methods are straining, pushing power usage effectiveness ratios to their breaking point, leading to exorbitant energy bills, physical limitations on data center density, and ultimately, a bottleneck on AI's potential. The traditional air cooling paradigm is reaching its thermal limit. To unlock the next generation of AI, we can't just move more air. We need to move the heat itself directly. This means a radical shift towards liquid cooling, pumping specialized fluids directly onto, or even through, the hottest components. Imagine a tiny river flowing over a blazing hot stone, carrying the heat away. This is the core principle. But these aren't simple garden hoses. They are intricate systems requiring extreme precision, novel materials, and entirely new manufacturing processes. This isn't just about making bigger fans. It's about fundamentally rethinking how we interact with heat at a microscopic level. And this is where the unseen heroes emerge: the specialized foundries and precision manufacturers. These aren't your typical factories churning out commodity goods. They are more akin to alchemists, forging the future of AI in environments requiring surgical precision. Building these advanced cooling systems demands techniques like microfluidic channel fabrication, where liquid pathways are etched with incredible accuracy into metal cold plates. It requires advanced material bonding, ensuring leak-proof seals that can withstand constant thermal cycling and corrosive fluids. And increasingly, it involves additive manufacturing, 3D printing complex heat exchange geometries impossible to create any other way. The secret isn't just what they build, but how they build it. Every component in these systems is a masterpiece of precision engineering. Take the cold plates that sit directly atop a scorching GPU. Their internal microchannels must be perfect, uniformly distributing fluid to maximize heat transfer, all while preventing cavitation or uneven flow. Then there are the manifolds, which guide coolant to and from dozens of these plates, demanding complex internal geometries and absolute leak integrity. The smallest flaw, a microscopic crack, or an imprecise bond, can lead to catastrophic failure, halting entire AI training runs. The materials are equally crucial: specialized coppers, aluminum alloys, and advanced polymers designed for thermal conductivity, chemical compatibility, and longevity. The margin for error is virtually zero. Beyond direct-to-chip liquid cooling lies an even more extreme frontier: immersion. Here, entire server racks are submerged in tanks filled with dielectric fluids, liquids that don't conduct electricity. In single-phase immersion, the fluid circulates to external heat exchangers. But in two-phase systems, the fluid boils directly off the hot components, turning into a vapor that then condenses and rains back down, creating an incredibly efficient, self-sustaining cooling cycle. It's like a refrigerator inside your computer. Manufacturing these systems involves fabricating specialized, sealed tanks, often from exotic plastics or stainless steels, ensuring fluid containment, chemical inertness, and easy server access. This isn't just about making parts. It's about building entire, self-contained thermal ecosystems. This silent arms race in specialized cooling manufacturing has profound consequences. It's not just about keeping servers from melting. It's about accelerating AI development, reducing its massive carbon footprint, and making advanced AI more accessible. Companies that can master these manufacturing techniques gain a critical competitive edge, pushing the boundaries of what's computationally possible. Countries that host these facilities become hubs of innovation. Without these breakthroughs, AI's growth would be hobbled by unsustainable costs, physical limitations, and chronic instability. The incentives are clear: innovate, or be left behind in the race for true artificial general intelligence. It shapes the entire future landscape of digital power. So, the next time you marvel at a generative AI, remember the hidden struggle beneath the surface. Remember the heat, the megawatts, and the intricate dance of engineering required to manage it all. The secret foundries of specialized manufacturing are not just building components. They are forging the physical foundations of AI's future. Their precision, their innovation, and their relentless battle against heat are precisely what will allow AI models to grow smarter, faster, and more efficiently. Without these unseen innovations, the grand visions of artificial intelligence would remain just that: visions, trapped in a furnace of their own making. This is the unseen, unsung battle, and it's just getting started.